So I think the main things I want to kind of focus on today are, what are the missing ingredients for confidential DeFi, and what are the things that people working on projects could be improving to kind of make it easier for the end user. And some of that will come from sort of like technical things. Some of that will come from sort of more like thinking about how people want to think about pricing confidential DeFi versus public DeFi. Okay, so there's sort of three kind of main topics I'm going to talk about in terms of things that could be done within confidential DeFi. The first thing is having a notion of modular privacy. And what I mean by this is virtually any financial mechanism has to have some public data, some private data, and some in-between data. In-between meaning some type of aggregation where you can't identify individuals, but you want the aggregation to also be accurate. And in some ways, I think one of the reasons it's actually quite annoying to write private DeFi applications is when you're a developer, you have to manually be thinking in your head about like which type of state am I interacting with, when am I crossing a border between private and non-private state. By crossing that border, am I leaking some side channel information about the actual underlying data? And designing systems in a way such that the end user, being a developer, doesn't have to think about that. The second thing is, what I kind of termed graded composability, and what I mean by that is, the idea of having homomorphic encryption is in and of itself a sort of form of composability, right? I can take the set of all the homomorphisms and I can compose them arbitrarily, and I still stay within a certain set of privacy guarantees. On the other hand, almost every DeFi application, as kind of mentioned before, has to go through some public data, some private data, and some sort of in-the-middle data. And you want to preserve those properties under composition even when you leave fully private mode. So for instance, if I do a calculation in FHE, and then I have to aggregate a bunch of FHE calculations, but in a, say, differentially private manner, I am losing some information, right? Like clearly I'm kind of leaking something about the system in that setting. But a natural question is like, how do I do that in sort of a minimal manner that preserves these properties? And the final thing that I think we'll talk about is how to think about resource pricing for confidential DeFi, and how do you ensure that users who want to pay more are able to, but also users who want the traditional public smart contract experience are able to also get the same thing. Okay, so these are all terms I made up, so if you don't like them, feel free to throw tomatoes at them. But modular privacy. So I guess one very simple axiom is you can't really have fully private finance. In general, finance needs some notion of disclosure from some set of participants to another set of participants. If there's absolutely no disclosure, it's very hard to find a clearing price. I did give some caveats of, well, people do use meme coins without thinking about the clearing price. But, in a lot of ways, most things in DeFi have some very clear public state, right? They quote you a price, they quote you a slippage, they quote you an interest rate. And if you have to have some amount of public state, you suddenly have a world where you have to think about, every time I cross the boundary between private and public state, how much am I leaking? In general, whether you're in the mechanism design side or in the pure finance side, generally there's almost always some notion of selective disclosure, where there's either a central party managing the disclosure or the individuals are able to disclose on their own. But I will say, despite this kind of being a sort of negative for like, you can't just do everything in FHE and you don't have to think about it, from the perspective of users won't use a fully private financial product, just mainly because they don't know what they're buying. Finance does do a good job of partitioning private state, public state, and state that is aggregated over many users. So public state, we all kind of understand that. Private state, we also generally understand that individual user balances, individual user state that's unique to them is quite important. But the important thing to think about DeFi and public DeFi right now is a lot of it is really based on computing aggregations across pools, right? You take a set of Uniswap v3 positions and I quote you a price and I quote you a slippage. You take a set of lending protocol positions and I quote you an interest rate. Now, that quoting action is something where you could do it in a sort of in-between fully private and not private manner, in the sense that I only need the aggregation to be accurate up to some quantity, and I'm happy to not know each individual position. So let's just take the example of CFMMs like Uniswap, constant function market makers. In a lot of ways, you can't really make them fully private, in the sense that, well, their public quoted price effectively tells you what the reserves are. So even if you did it privately, it sort of has this kind of problem. But it's actually quite easy to make statistically private, both in a differential privacy manner as well as in a k-anonymity set privacy manner. And the most interesting thing about turning CFMMs into private mechanisms is there's actually a very clear notion of how much extra the user is paying. So the user either pays an extra fee, so the last theorem that I cite here, which is from a paper that analyzes sort of the notion of users paying their own fee for private CFMMs. There's sort of a notion that the user has to make some notion of, hey, I want more privacy, but I'm willing to pay up to some rate for it. So what this sort of suggests is a lot of DeFi probably could take advantage of things, provided that, privacy preserving technologies, provided that there's sort of an easy interface to go between private and non-fully private state. So one way I like to think about this is that there's sort of three very high-level types that exist in all privacy-preserving smart contracts. There's a fully public type, of course. There's what I would call the algebraically private type, that is what you're doing in MPC or FHE. And then there is the statistically private type, which is I'm taking an aggregation across some private calculations and publicly posting the aggregation. Being able to actually write code in a way that you can move between these three types in a kind of seamless manner is actually, I think, one of the reasons that we haven't seen a lot of DeFi applications write their private versions very easily. In some ways, it's very hard for the developer who doesn't really necessarily want to understand how their, A, how their state is being made private, and B, what happens when they cross the privacy boundary, where they promote or demote their state from private to not private. And I think one important thing to think about is how do you design programming languages such that this is a thing the end user doesn't have to think about. They can, mark particular types as private, they can mark particular functions as private, but then they can also get statistical aggregations with some guarantee. Okay. The second thing I think that's actually kind of very important for thinking through DeFi applications in particular is this notion of how composability changes when you move between private and non-private state. So, different types of privacy sort of inherently have different types of composability. So if I start in FHE, and I apply a bunch of functions, my private state stays private. If I start in the public domain, my public state stays public. On the other hand, whenever we do these kind of aggregation-like actions, we have much weaker guarantees for composability. So I put 3 kind of high-level theorems at the right that show you how composability degrades when you have statistical privacy versus kind of pure privacy. What these kind of degradations tell you is that, hey, actually, when you're in statistically private mode, you can't really compose too aggressively. So I can't take 5 Uniswap pools prices that are computed in a differentially private manner and aggregate them without incurring some function, probably roughly 5 times the loss. That's sort of what the first theorem says. The second one says you can do slightly better than that. But the main point is that when you're a user who is a developer writing code that is meant to have these financial transaction implications, you might not be thinking about, oh, actually, this price that I'm quoting, if I combine it with another price and then use it as an oracle into another protocol, I've just multiplied my error by 2 or 3 times. This is actually extremely important within DeFi. This is actually, I think, a thing that I think people who are working on pure privacy-preserving technologies kind of underestimate about the difficulty of writing, the most popular applications is people tend to take outputs that are aggregated from one protocol and input them into another without thinking about the error, kind of the implied error rate of that particular input. So this notion that this kind of statistically private data is only partially composable is actually a very important thing that the user hopefully doesn't have to think about, but they definitely have to deal with. The other thing that's worth noting is that statistically private mechanisms always have sort of non-uniform composability guarantees. For instance, addition and multiplication have very different guarantees in terms of the error rates. So I think you should sort of think about how users who are writing these types of contracts should be thinking about things, is that there's sort of some notion in which when they demote or promote state from public to private, they're demoting or promoting the types of operations they can do on that state. And if the user is not very aware of that, then they can very easily give themselves wrong sort of output. And I'm certainly not a person who likes category theory very much, but I did unfortunately draw a commuting diagram. And I would say that there's sort of this natural thing that somehow users who are developers need to be aware of which state they're in. So you could imagine being in a debugger and you're traipsing through a sequence of function calls, and you see a function call that says, you notice that something is off by a factor of 2. Imagine if you could actually identify that, hey, this is because I added this particular statistically private data to this fully private data. And in the process, I promoted the fully private data type to a statistically private data type, which causes an error of up to X because I add some noise to the input. I think there's sort of a notion in which we should be thinking about composability across private and not private state, because it's actually a thing that trips up developers a lot when they try to make private DeFi applications. So one reason to think about it in terms of this sort of grading type of thing, when I say grade, I sort of mean in the mathematical sense for algebras, is that if you actually, if sort of this notion of like going from FHE state to differentially private state and going back to differentially private state sort of composes, you kind of have these errors commute, it sort of ensures a notion of minimality. So you're sort of only promoting the types, the minimally weaker representatives. So like I take a fully private state in FHE, maybe I promote it to a differentially private state. How do I figure out what the minimum noise I have to add is? this is the type of stuff that a compiler should be doing, not the end user, right? And so by thinking of when you cross these boundaries between private and not private, you can think also about the guarantees the compiler can give the end user. And so that's sort of one thing I've observed people run into a lot of problems with when they're developing private DeFi apps, is that they really can't keep track of some of the error tolerances that they're dealing with. Okay, so the final thing I want to talk about is sort of a very simple observation, but hopefully one that is somewhat non-trivial, which is when you think about private DeFi, you have to think a lot about resource pricing. The resource pricing is highly non-uniform. And so when I say non-uniform, I mean that the cost of private state versus public state is different. The cost of statistical state versus private state is different. Statistically private state, that is. And obviously the same is true for execution. So the question is, to the end user who doesn't really care about how you allocate their program, they just say, hey, I don't want to pay more than X% than the public version. How do you kind of think through how you deliver that? So I think there's sort of roughly three kind of problems you really care about in confidential DeFi, which is user state is minimally revealed while efficiency is minimally reduced. So there's sort of this kind of idea that some user state has to be revealed to compute these aggregations. But at the same time, you also don't want the efficiency of kind of adding the extra private overhead to lower the welfare worse than some amount. The final thing is that I think users would like to be able to choose a desired level of privacy and then just have a protocol ensure it meets those guarantees, versus them explicitly saying, I want this particular state private and I want this particular state public. Okay, so I think a maybe more symbolic way to think about it is, let's think about kind of this overall optimization problem that tries to satisfy those goals. So imagine we have some notion of an efficiency function, which sort of measures the efficiency of a DeFi protocol. So how efficient the pricing is, what's the difference between the optimal price and the average price, what's the difference between lending protocol quoted interest rates, some function. This function takes in some state, either private, public, or statistically private, as well as some hyperparameter theta. You can think of the hyperparameter as dictating a user's choice of, I want K bits of security for this particular state, I want Y bits of security for this other piece of state. Now imagine you have these sort of, and so that's the first thing. The second thing is, yes, these hyperparameters. The third is sort of the valid state that you have in the DeFi protocol. The PI operators you can think of as projection to fully homomorphic state. So I take the public blockchain state, I put it into a private shielded mode, and it never leaves the shielded mode. So the end user, the outside world doesn't see X, it only sees PI of X. And then finally, I have the notion of statistically private state. So this is sort of the notion of, hey, I added a bunch of noise to the prices so that you couldn't identify a particular user's impact. And finally, we have some notion of what's the efficiency loss. So this function C of theta kind of tries to capture this notion of, hey, I'm going to take some efficiency loss, C, for providing privacy. What is my efficiency loss when I look at this maximum? So the end user does not want to think about that, obviously. But I do think the end user cares about answering queries of the following form, which is, I'm willing to pay more than 20% more for some amount of privacy. I put it in bits, but choose whatever way you want to represent that to a user. And I don't want to lose more than 20% efficiency. So I don't want my quoted price on Uniswap to be 20% worse. I don't want my interest rate to be 20% worse. There's a sense in which you can write that as an optimization problem with constraints. right? So if you actually have the resource prices for the different pieces of state, you can actually try to turn this into an optimization problem and then figure out which pieces of state need to be private. I think in the long run, this will end up being how the average developer interacts with FHE or ZK, more so than what we have now, where like you really have to keep track of all your state. So the last thing I want to kind of mention is there's sort of an extreme version of turning confidential DeFi into an optimization problem, in that it sort of might look like what people want out of intent marketplaces. You can have solvers who, instead of trying to find an optimal routing, offer users discounts if they provide data for an aggregation. So, if users are able to be like, hey, I'm a liquidity provider, I'm willing to quote this particular range, I'll publicly reveal that I'm willing to quote that range to you, but only if you add it to an aggregation. So, so that front end could say there's this much liquidity, even though no one can identify the LPs. You could also imagine that the users are effectively running a Dutch auction for their sort of notion of cost of privacy. So they're trying to find the minimal price. They start at a high price, which is the fully private mode, and they decrease their price until they find the right price they're willing to clear at. And the final thing is that this optimization problem is solved off-chain, just exactly as we see in the rest of DeFi right now, with the intent markets doing that. And with that, that's it.
So we have time for maybe 2 questions.
Hello, thank you for the presentation. I have a question regarding on the slides 21, so one previous before this, and you mentioned that the value of C theta should be bigger than 0.8 in order to preserve the privacy, if I remember correctly.
C is efficiency. So C is
efficiency.
Efficiency relative to the public mechanism, yeah.
Is there any particular reasons why you just like C theta to be like bigger than 0.8?
Oh, sorry. I give an example of a user query, which is like, hey, I'm willing to pay up to 20% more for efficiency greater than 0.8. So I just wrote that as an example. But the idea is like the end user would give you these parameters, right? They give you imagine you gave them 3 dials of like, how much efficiency do you want? How much privacy do you want? What's your slippage tolerance? And then you would basically construct an optimization problem, figure out how much private state and statistically private state, and then execute.
Okay, that makes sense. Thank you very much.
Thanks for the talk. It's very interesting and thought-provoking. On the notion of k bits of privacy, I mean, some, different pieces of data, each piece of data has a totally different value in terms of bits. How do you, what's that notion in this optimization problem? And then another question I have is, given this market bit of choice, one of the thoughts I had a lot about privacy is always seen as a public good, which means it leads to market failure, and there needs to be some kind of a public subsidy. And in a marketplace, like allowing users to choose that, it's sort of a selfish intent that sort of creates that market failure. Where's the optimization? And then the third question, sorry, a follow-up to that is, in a competition for TVL, right? It seems like this inefficiency seems like it's something that the current landscape may not want. So how do we get to that happy middle layer?
Good question. So the first one is actually, there is a sleight of hand in this hastily written optimization problem, which is I put no constraints on PI and SPI. But that's not really realistic, right? Like, there might be some state you just will never make private, so there'll be some constraint that the projection can't project that into private mode, right? So the constraints will actually define which places your trying to define your notion of privacy on. The second sleight of hand is I obviously just simplified this and put a little factor A in front of the statistically private piece, which is just meant to be the relative value of X bits of, say delta epsilon differentially private state versus X bits of FHE state. So it's a good catch that I kind of hid a lot of those details. The second thing is you talked about the public good subsidy aspect. So this is why I actually think the solver marketplace is a little bit better than a blockchain for kind of facilitating privacy, and that the solvers, if you think about payment for order flow right now, the solvers pay the wallets, and then the wallets give them aggregations, and then they use that to decide how much to trade. There's no reason that the solver couldn't go straight to the user if they were able to do it fully privately, versus the user having to basically trust their wallet. And so that's kind of what I mean by like the solvers offer users discounts. It's just giving the payment for order flow direct to the user instead of to the, and I think that potentially, I'm not saying for sure, is sufficient of a subsidy. Because like you already see this with CalSwap and Uniswap X, where users definitely are optimizing for who's giving them the biggest discount. And so the discounts are coming from the solvers who have better information. And if the users could sell their order flow sort of like in the right time and for cheaply, I think people would basically be paying for this discount. So, and sorry, there was a third thing, but I forgot. Sorry.
I think it was on TVL.
Private TVL versus public TVL. Yeah. This is, again, why I think the off-chain stuff is a little easier to do, to convince private usage of private TVL. And also these kind of off-chain markets, like the intent markets, are sort of separated from the TVL game to some extent. Like they're related in that people need some assets to fulfill orders, but most market makers' wallets, if you look at them, who are fulfilling intent orders, their wallets are not growing as fast as sort of like the market beta. So
Great. Thank you so much, Tarun. This was incredible.